So light of wavelength 750 nanometers passes through a slit 10 micrometers wide and projects a pattern on a screen that's 20 centimeters away. So for part A, what's the frequency of the light used? So just a real simple equation. F equals c over lambda. C is 3 times 10 to the 8th. The lambda is 750 nano, which is 10 to the minus 9th meters, and that's equal to a frequency of 4 times 10 to the 14 hertz. For part B, determine the angle the light makes for the first dark spot in this pattern, and say if the small angle approximation formula can be used. So we want to take the equation d sine theta equals m lambda and rearrange this for theta. So just divide both sides by d and then take the inverse sine. So theta is the inverse sine of m lambda over d. That's the inverse sine of m is 1 because it says for the first dark spot times the wavelength, which is 750 times 10 to the negative 9 divided by the distance, which is the width of the slit, and that is given as 10 micrometers, and micro is 10 to the negative 6, so 10 e negative 6. When you plug all that in, you get an angle of about 4.3 degrees. That's a pretty small angle. I usually say the general rule is about 10 degrees or less you can use a small angle approximation, so we'll say that yes, we can use it. For part C, determine the width of the central maximum. Now you know that when you shine a laser through a single slit, the pattern looks something like you have a kind of a wide bright spot in the middle, and then there's some lesser spots as you go further out. So it looks something kind of like this. And this question is asking you to determine the width of that one right in the middle, the central maximum. So the way to do this is, if you think about what the equations give you, the small angle approximation formula, which is xm, is approximately equal to m lambda L over d. This equation gives you the distance for a single slit to the mth dark spot. So it's the distance from the center, right here, over to that first dark spot, right here. That would be your x1. So to get the width of this whole slit, you just take that number and double it, because it's going to be an x1 distance on either side. So the distance to the first dark spot on either side, that would cover the whole central maximum. So let's go ahead and plug in some numbers. So x1 is going to be equal to 1 times the 750 times 10 to the negative 9 times the L, that is the distance to the screen, which is 20 centimeters. 20 centimeters is 0.2 meters. Remember, we want to put everything in standard units, divided by the D, the width of the slit, which we said was 10 to the negative 6. So that gives you an answer, when you plug all that in, of 0.015 meters. To put it in slightly better units, we'll move the decimal 2 places over and say it's 1.5 centimeters. Now keep in mind, what we found is just this distance x1, which is half of that width of the slit. We want the width of that central maximum. We want the whole thing, so we just want to take that 1.5 and double it. So we can just say that the width of this whole thing is 1.5 times 2, or 3 centimeters. In part D, draw and label a graph of the light intensity versus position for the pattern that is produced on the screen. So just to kind of reproduce that pattern that showed up, I'm going to put it directly beneath this graph. We had the one kind of longer central maximum right in the middle, and then it kind of trailed off into some smaller bright spots as you went further out on either side. So something kind of like that. So to draw a graph of intensity, I'm just going to put the graph directly over top of where these spots are. And so the first one, there was a bright spot that kind of went from there down to about there. And you see where it gets to the dark area, the graph is dipped all the way back down to practically 0 intensity. And then the next spot over had a little bit of intensity, still a decent amount, but not as much as the first one. And then it goes back down to a dark spot, and then a little bit less intensity, and back to a dark spot, and then less intensity still. Same thing on the other side, it's just symmetrical. So the graph looks kind of like that. And you can see that I've lined all of the places of 0 intensity up with one of the dark spots in this pattern that I drew directly beneath the graph. And I'm also going to label the graph with the distances. We know that for a single slit, the distance you calculate for xm is the distance to the dark spots. So each of these dark spots, which is right here, is going to be what we got for xm, which was 1.5 centimeters. So I can say this right here is 1.5, and then to the next one, that would be an additional 1.5, so it would be at 3.0, and then over here would be at 4.5. Same on this side, we're going to have a 1.5, this would be the 3.0, and then down here would be the 4.5. So that is for part D. And then for part E, we want to know the distance between two adjacent bright spots on one side of the central maximum. So in other words, something like the distance from this bright spot right here to this one right here. So we'll say the distance from here to here. So m equals 1 corresponds to this spot right here. M equals 2 corresponds to this dark spot right here. So this bright spot will be halfway between. So this is like about 1.5, and then this right here is about 2.5. So the change from 1.5 to 2.5 is just is just 1. So I'm going to write down the same equation we've been looking at, which is the xm is approximately equal to m lambda L over d, but it's important this time to put some deltas in there because we're talking about the distance between two things. So the delta x represents the distance between two bright spots, and the delta m represents the distance between, in this case, is going to be two adjacent orders. So this will be equal to the delta m, which we said that distance is 1, not the distance, but the distance between the orders is 1, times the lambda, which is 750 times 10 to the negative 9, times the L, which was 0.2, divided by D, which is 10 times 10 to the negative 6, 10 micrometers. Notice that this is the exact same equation you did in part C when you got an answer of 0.015 meters, which is 1.5 centimeters. So in other words, this distance from this bright spot to this bright spot exactly matches the distance from the center to the edge of that central maximum.